Hi, everybody. In this video, we're going to start talking about the electron transport chain. So we're going to describe the components of the transport chain, not exactly what happens in the transport chain, but what they are and how they look like. So the fundamental reaction is, again, we got all the electrons from the TCA cycle in the form of NADH, and eventually they're going to be passed on to oxygen. And that will of course generate NAD plus, and then the oxygen will become water. But this is not happening in one step. This is the grand sum of the whole reaction, not the many individual steps. Okay, so as we've seen in many pathways, there are many those individual steps that come up to this general overall reaction. So the first thing we need to discuss is how does the respiratory chain change the proton motive force. Okay, the main job of the respiratory chain, of the electron transport chain, is to charge our batteries, right? To change the proton motive force. So how does it do it? In principle, how could you do it? This is the mitochondrial, the inner mitochondrial membrane. That's this line here. This is a hypothetical scenario. The N side is the matrix, the inside, the inside deep in the mitochondria, where the NADH is, by the way, okay, from the TCA cycle. And the P side is outside of it's in the intermembrane space between the inner and outer mitochondrial membranes. So again, the overall idea for the electron transport chain is that when it moves the electrons from NADH eventually to oxygen, that it has a lot more protons here on the outside. Okay, so that is what will generate the proton motive force. This is what will charge the batteries, literally. So how can you do this? Okay, so you have one reaction shown here, and you have the electrons, and they go find their way on some acceptor. If you do that, okay, have you changed the pH, the proton motive force? Have you changed the pH essentially? Yes, between the inside and outside. The answer is no. Okay, so you put them on the same side here as I have shown them, both on the P side, and the net change. From the first reaction you get 2 protons, but then you consume those 2 protons in the next reaction, so you end up with 0, right? So if you have arranged your redox reactions in this way, you get 0 proton motive force. Okay, so that's not a good scenario, obviously. So if, however, you put them now on opposite sides, okay, you have the reductant and the oxidant. So you have your first, let's assume this is an NADH, you make an AD plus. The 2 protons are coming off on this outside side. Then the electrons find their way onto the acceptor, and the acceptor also picks up 2 protons, and you reduce it, the acceptor called shown here as Y. And by doing so, you generate 2 protons on this side, the P side, and you subtract 2 protons from the inside. All right. So the delta P is actually you're gonna generate a proton motive force. You're gonna have a net change of 4 protons, obviously. All right. It's as if 2 protons left the inside and moved to the outside. So you have to, when you tally them, you have 2 more here, 2 less on the other side. So you have a net change of 4 protons. So that is a redox scheme that can actually generate a proton motive force, right? And again, this stuff happens only when you have membrane-bound reactions, which all the electron transport chains are in the membrane. Okay. If you put them, you can have the reductant and the oxidant on the same side. In this case, again, you put them on the inside. This is assuming this is an ADH. Sorry, this will be an ADH. So the 2 protons leave an ADH. And instead of being deposited on the same side where the NADH was on the inside, somehow these protons come out, okay? And then the electrons find their way to the acceptor, and the acceptor picks up another 2 protons, and again, you have a proton motive force generation, again, with a net change of being 4, right? So depending on how, where you put the protons and the electrons in this scheme on which side of the membrane, then you can have a generation of voltage across the membrane, essentially. Of course, you can also have a proton pump, okay? And you can do your redox reaction and that couple that with some pumping action. And then that takes out the protons from the inside, puts them on the outside, and you generate a net change again. So all these possibilities are there, and pretty much all of them happen, okay? Now, how many electrons, we have to also count the electrons here, how many electrons do we need to reduce oxygen? You know, in water, you have one atom of oxygen. So if you have dioxygen, you start the whole reaction with half a molecule of oxygen. So for that one atom of oxygen, you will actually need 4 electrons to fully reduce it in the form you find in water, right? So that's another accounting that we have to do when we see at the very end how oxygen actually gets reduced. All right, so now let's discuss the parts that we find in the electron transport chain. So these are cofactors. We've already seen some, actually only one, this one up here, flavoproteins, and they are bound to big protein complexes, right? And these protein complexes are proteins and many of them to form one complex. But the prosthetic factors, the cofactors in those complexes are that actually do the business of moving electrons around are those cofactors here. Okay. So flavoproteins like FAD, we've seen them before, and they can move 1 or 2 electrons. Remember NADH, so where the electrons are found in TCA, from the TCA cycle, always moves 2 electrons. It's a hydride ion transfer, so you have a proton and the 2 electrons that go. But flavoproteins, they can either do 1 or 2. We saw this in the pyruvate dehydrogenase reaction. Okay, so that's very special. Likewise, coenzyme Q, which we have not seen, but we're going to describe in a minute, also can transfer 1 or 2 electrons. So those are kind of special. Okay, they're really adaptable to 1 or 2 electrons. Then we have all these prosthetic groups, hemes and cytochromes that I'm sure you've heard before. Those, all of them here, they move 1 electron only. Okay. We have iron sulfur proteins, so we start seeing some weird metals, iron, we see copper, and those move, again, those are bound in specific configurations in the proteins. They are cofactors and they are found in proteins, and the proteins assemble all together in a giant complex for each one of these electron transport complexes. So we have metals, as I said, down at the bottom here, and up here with flavoproteins and coenzyme Q, we have aromatic rings and double bonds. So kind of more familiar of the things we have seen. We have not seen metals yet in the class. All right, so this is, you have seen this slide before. This is a classic flavoprotein, of course, FAD, and we've seen the cycle again before. This is the business part here in the middle of this tricyclic ring system. So the middle ring with the 2 nitrogens, and depending on whether you engage 1 or 2 of those nitrogens, you can move 1 or 2 electrons. Okay, and there they are. All right. FAD, of course, this is the business part of the molecule, but it's a little bigger. It's got the adenine and the ribose right at the bottom here. But there is another simple version and cousin, so to speak, of FAD called FMN, which lacks this tail end here of FADH. But the chemistry for all our purposes is exactly the same here, moving the electrons 1 or 2 electrons at a time with the same ring system. All right, this is coenzyme Q, ubiquinone. Again, you can buy this in at nutrient supplement areas of grocery stores. It's a very important component in the whole respiration and electron transport chain. It can move 1 or 2 electrons. Okay, so just like the flavoprotein components of the electron transport chain, this coenzyme Q can also move 1 or 2, depending on whether it's in the fully oxidized form. It's going to be in the keto form, okay, ubiquinone, And in the reduced form, these oxygens will be in the hydroxy state, so alcohols, and that will be the ubiquinol. What's super special about coenzyme Q, and I want you to remember, is that it's actually lipid. It likes to be in the lipid environment, inside the lipids, essentially. So this will be the membrane, the inner mitochondrial membrane, where the protons will get distributed across this membrane to generate the proton motive force. So Q, coenzyme Q, is extremely unique because this is where it lives, okay, inside the lipid bilayer. Okay, so that would be the inside and of the mitochondrion, the matrix, and then again the idea is to pass protons from the inside to the outside, so you can generate proton motive force. All right. Then we move to cytochromes, which all it means is really a colored substance. That's it. Cyto is cell, chrome is a color, so it's a cellular colored substance. They come in many different varieties, and people have been purifying them for 100 years or more. They are heme-containing proteins. So cytochromes are proteins, and the cofactor in those proteins are hemes. And how does heme look like? You'll see in a minute. But all hemes, in this case, have an iron atom in them. And iron comes in many different oxidation states. For anyone who's been in the Southwest, have seen the red cliffs and you might think in Grand Canyon. Actually, here the background that I have in my picture from Monument Valley, it's red because of the iron present in the minerals there, in the rocks. We don't deal with all these oxidation states in biochemistry. So as I said, there are many for iron, but in biochemistry we only care about two. So the ferrous and ferric. Okay, the more ferrous, of course, is the reduced ferric is the oxidized form of iron. In this case, for biochemical settings. So what's important here is not so much the how many electrons and all that are there, but whether they are paired or not in the spin configurations in the orbitals of the iron atom. So if you you look at some different configurations here in iron 2 and iron 3, and its little arrow here is supposed to be an electron. And if you go and count the ones that are not in pairs, so the single electrons in various spin states, so we have the high and low spin states. So in these different states of iron 2 or iron 3, if you go and count the single electrons, we have 1, 2, 3, 4, 5, 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 unpaired, okay, electrons in iron 3. If you count the unpaired electrons in iron 2, you find we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So one less, okay? So why is that significant? Well, the fewer unpaired electrons you have, then you are in a low spin state. Why do we care about the spin state? So, which means, of course, that iron 2 is in a lower spin state than iron 3, okay? If you are in a low spin state, the iron molecule, the iron atom, which is a giant atom, okay, as far as atoms go, is more compact, okay? So it takes up less space in the low spin state. So the iron in iron 2 will take less space compared to the iron in iron 3, because iron 3 has an extra unpaired electron. The more compact the iron, or the spin state of the iron now, if it's imagine you are the protein and you're hugging an iron atom. This iron atom can either get bigger or smaller depending on the spin state of the iron. But if it does that, okay, it's going to push the protein. So the protein actually, it will change conformational chains. It will change its conformation. It's going to be in a more open conformation, let's say, when it gets pushed out by a high spin iron, let's say, which is bulkier. All right, so this is a heme B, and this is how iron is coordinated here in heme. And depending again on the spin state of the iron, okay, this is shown here as iron 2, it can be iron 2 or iron 3. this essentially, this heme, it changes its occupancy space there. So this is how it looks when it's bound by one of these cytochromes. So the green thing here are the amino acids of cytochrome C, one of the cytochromes. It's a small protein, and it binds heme. And right in the center here, we have, of course, iron. So imagine now that this iron, okay, it literally pushes and opens and closes, or not opens and closes, but expands and contracts the protein. Okay, it's as if the protein is breathing, depending on how many electrons are on this iron in the low spin versus high spin state. But that's not all the iron we have in cytochrome C. Many proteins of these electron transport complexes, or I should say, so cytochrome C is a solo protein. It likes to be on the aqueous environment, touching the membrane, but on the aqueous environment. So it's a different situation from coenzyme Q, which likes to be in the lipid environment of the membrane. So we'll see this player again in cytochrome C. But iron, I mean, that's not all the iron we have, not only in cytochrome C. All these hemes, they exist, all these irons exist in many other components of the electron transport chain. We have iron sulfur clusters. So you have the two irons here, and we have the various sulfur atoms coordinating them, and so you can go back and forth with the oxidation state of one of these irons. We can have 4 and 4 irons, 4 sulfurs, so that's a typical iron sulfur cluster shown here. Depending on how many of these irons are in the ferric versus the ferrous situation, you can set up your redox reaction here. In bacteria, it can be in a different form, but there are many of those. Okay, the iron sulfur clusters. Lastly, we have in the last enzyme in complex 4 that actually does the reduction of oxygen to water. We have copper. We have a copper oxidase. Okay, that's again, it's in complex 4, and copper also exists in this case in 2 oxidation states that we care about, the +2 and +1. And if you see all of them, where they are in a variety in this major electron transport complexes, which we have 4. Okay, complex 1, complex 1 oxidizes NADH. Okay, and complex 2 receives electrons from FADH, and we saw that in the TCA cycle already. Okay, and complex 1 and complex 2, what they're going to do is they're going to transfer their electrons on coenzyme Q. So the chain doesn't go from 1 to 2. It's either 1 or 2, and the electrons are found on Q. Then Q passes the electrons to complex 3, okay? And then we go on to complex 4, and this is where copper is found, and this is where we actually have the reduction of oxygen to water. So these giant complexes, this is the mass, these are proteins, obviously, giant protein complexes. You see how many different subunits they have. So complex 1 has at least 45 different proteins that make up this complex. Now you see what they're called complexes. Complex 3 has 10, 13. And the prosthetic groups, the ones that we're talking about earlier, okay, where actually the electrons are found, we have flavin proteins in complex 1, some more flavin proteins in complex 2, and iron sulfur clusters. Then we have the hemes, and then we have more hemes, in complex 4, and copper obviously is, as I said, is unique to complex 4. The source of these electrons, okay, complex 1 again is NADH, complex 2 is succinate. For that reaction, the TCA cycle that generates FADH2, and both of them, okay, they pass it on to Q. Okay, so Q gets reduced, and by either complex 1 or complex 2. And then what happens? Q will through the action of complex 3, will pass its electrons to cytochrome C. Cytochrome C again was this little, this little protein that likes the aqueous environment. Remember, Q likes the lipid bilayer, but they work together here. And with complex 3 again, what complex 3 does is to promote the transfer of the electrons from Q to cytochrome C. And then cytochrome C brings the electrons to complex 4. Okay, cytochrome C gets oxidized. And so the whole thing can start again. Okay, so and complex 4, that's a terminal reaction there. It would pass on the electrons to oxygen. Okay. So this is what they do. This is how many different proteins are in each of these complexes, and this is the various prosthetic groups. Now, you do see a pattern here. So you don't see the flavin, let's say, prosthetic groups in the later complexes. Okay, and there is a reason for that, because if you actually see, let me pull myself a little bit. If you see again on the E values, back to the E values, where we find all this compounds, you see that NADH again it was about minus 320, so somewhere there. And how do we get NADH? We get from TCA cycle, we get some from pyruvate and other sources in the cell. And then we have the flavins. Okay, so that's complex 1 and complex 2. And they are more positive. Remember, the electrons flow from the more negative, the rich get richer, so in terms of reduction potential here. So the more negative you are, you tend to pass them to something that's more positive than you. So NADH will pass them to flavin prosthetic groups. And then you have the iron sulfur clusters that are even more, a little more positive. Then Q is a little more positive. The cytochromes here are a little more positive. And at the very end, you have oxygen, which is the most positive of all and wants to receive all these electrons. Okay. So that's a general idea. Again, it makes complete sense based on the values of these prosthetic groups, and you see why they flow in the way they flow. In terms of how many electrons are moved, I already told you, that we have 1 or 2 electrons with the flavin cofactors. And here is again the E value. Again, you go from the more negative to the more positive one, which is of course oxygen again at plus 800 millivolts. And once you are in the cytochromes and you have 1 electron moving at a time. Remember, at the final step, it takes 4 electrons to reduce oxygen, as we discussed earlier. Now, since oxygen reduction happens the last step, what's the point of all the previous steps, right? I mean, why do we bother? So what's the point of respiration? Again, you have to remember this. The point of respiration is actually to charge the battery, to build the proton motive force, right? So in all these steps, that's the task, to couple this electron transfer with what is not shown here, which is the proton transfer from the inside of the mitochondria to the outside. Okay, that's what charges the battery, and that's the point of respiration. How is that achieved? These are the complex, again, complex 1, 2, 3, and 4. So the electrons from NAD through complex 1 will reduce coenzyme Q. And if you don't have NADH, but you have, let's say, FADH from succinate here that we saw earlier from the TCA cycle, those will get passed on to complex 2, okay? And complex 2 will put them on Q, so will reduce Q. So Q is getting reduced, which again you see it in the lipid bilayer here. That's where it likes to be. Q receives the electrons from complex 1 or complex 2. Again, a classic confusion, which let's dispel it now, is that you go from 1 to 2 and then to 3 and 4, all this complex. That's not the case. You are either 1 or 2. Okay, it's a fork on the road, and if you are an electron, you either take this, complex 1 or complex 2 to find your way onto Q. Once you are on Q, then complex 3 will transfer the electrons from Q to cytochrome C. That's the little protein that's in the aqueous environment, on the outside of the membrane, actually. And then pass them on to complex 4, and complex 4 will eventually pass them on to oxygen, and you got water. Now, notice the little arrows here. The point of doing all these steps, again, is so that protons move from the inside to the outside. And that's what builds the proton motive force. Okay, so you see complex 1, 3, and 4 all generate proton motive force, electrogenic. Complex 2, on the other hand, does not. Okay. And the more protons you have, you move across the inner mitochondrial membrane, the more charged your battery will be. And then when you bring them in through complex 5 or ATP synthase, when you make ATP, the more ATP you make. The higher the difference in voltage here, the more protons you will have on the outside and the more ATP you will make. So what you notice here is that the electrons that come in through complex 2, okay, at that step, we don't have any net movement of protons. You get later from Q, to go to 3 and 4, you have some protons. But if an electron starts in complex 1, it will actually generate more of the protomotive force. It will be more, you have more of energy output in the end in terms of ATP. But for those electrons that come through complex 2, you miss this first step. So you charge the battery a little less. We'll get back to that point. It will make more sense later. But that's the basic idea, okay? Yes, the process is complex. Yes, it involves all these many different cofactors, iron sulfur clusters, flavin cofactors, Q, cytochromes, and copper oxidases here. But the point is that you do this in all these multiple little steps so that you can have a net transfer of protons and you can charge your battery. Once you have a lot of protons on the outside, those that can come back in, they want to come back in, very, very badly. That's the point of the chemiosmotic principle that Peter Mitchell discovered. And once you couple all this electron transfer with the proton movement and you charge your batteries, that's how you make ATP. Okay, then you have literally built up all the energy, more something like a dam, that generates electricity. You have a huge amount of water on one side versus the other side of the dam. The water wants to go through, kind of like this. This is how it works with the protons. They want to go through, and that energy is captured here, so you can make ATP. Okay, that's a beautiful insight that Peter Mitchell had, again, that gave him the Nobel Prize. And it's a fundamental insight because, again, in the 60s, everybody thought that ATP was made in something analogous with the glycolytic enzymes. People thought that these reactions here with complexes, you have something like this with phosphorylations and so on and so forth that we had seen in glycolysis, and that's how you make ATP. Well, Peter Mitchell clearly showed that that's not the case. Okay, it's a very different principle. And again, it doesn't matter what ions you do pump or you move across. It could be sodium, as we have already seen in one case. That's another way to charge your battery. The complexes could be different, processes could be different. As long as you move them across, some ions across the membrane, then you can make ATP. All you have to do is just stick your ATP generator right there, and you're going to generate ATP. And so that's the general idea of the electron transport chain, and these are the various components. We're going to discuss them in more detail in later videos, but before we close this presentation, I saw them here as independent, the complex ones, separate from each other, as if they are far apart. And they can be far apart, by the way, because how do they get communicated? Q will find its way from 1 to complex 3 and so on and so forth. The same thing for cytochrome C. So they don't actually have to be touching each other. Okay, you have these little molecules, coenzyme Q in the membrane and the cytochrome C on the aqueous side, on the outside to move the electrons around. Excuse me. I had to sneeze. All right. So, and that's how they are. But somehow, if you isolate these complexes, let's say from hearts of cows here, you find them in some cases all together. They all come together, and this is one view with cryo-electron microscopy. I think this is a better view here. And you can see all the various complexes shown in different colors. I believe this is 1, this is 3, and this is 4. So yellow will be the one. It's the biggest one. Remember, it had at least 45 different proteins. Complex 3, I forgot how many had, maybe 10 or something, and complex 4 had 14. And they all come together. They all appear to be coming together. And that's how it looks like. So remember, 1 will pass the electrons to Q, and then 3 we have cytochrome C, and then from C it's going to go to 4, and you see them all coming together. So you have this super complex now. You have one complex here, one giant complex, another giant complex, and another giant complex, and all of them come together now in a giant super complex. So super complexes, it turns out, and they're called respirations. We all get them, but they're dynamic. Okay, if you're sitting around you don't make, you don't assemble them into these giant supercomplexes. But when you exercise, especially endurance exercise, then you see formation of these supercomplexes. So they all accumulate together. So the presumption is that it makes them more efficient. Okay, so they work better if they're all distributed as supercomplexes, which makes sense. How exactly that happens is not clear, but they do come together in supercomplexes. All right, so that's the giant, now that's the simple schematic of the electron transport chain. Again, NADH that we saw how we get it from the TCA cycle. Um, the electrons from NADH, the job of complex 1 is to pass them on to Q. So it reduces coenzyme Q. So we got from ubiquinone to ubiquinol here from complex 1. If you don't have these electrons, if you have them, the FADH, if you have them on FADH, and we saw how we get some in one reaction at the TCA cycle, then through complex 2, those electrons will find their way onto Q. Okay. Complex 1 does affect the transfer of some protons. Okay, so it is electrogenic, it will charge your battery, but complex 2 does not. Once they're on Q, these electrons, where they're either from complex 1 or from complex 2, but not both, okay, then through complex 3, they will be passed on to cytochrome C, and the cytochrome C will pass them to complex 4, and complex 4 will pass them on to oxygen, and finally you got water out of there, and you reduced oxygen. So that's the whole series. We'll stop at this point with this video, and then we'll start describing each one of these complexes in more detail.